So we move into something called homogeneous equations. We've seen these equations before. These are linear equations. So just to go back and reiterate, a linear equation of nth order is anx, nth derivative, an minus 1, n minus first derivative, an minus 2, n minus second derivative, all the way up to the first derivative, and y equals some g of x. If g of x is 0, then the nth order linear DE is called a homogeneous equation. And always you've got to keep in mind that a sub k of x for k equals 0, 1, 2, all the way up to n, they're all functions of x, or in general, functions of the independent variable. So homogeneous equations simply have g of x is equal to 0. One of the most important things in terms of notation is the differential operator. The differential operator is denoted by uppercase D. What does that mean? So if we have dy over dx, we can simply write it as d times y. If we have d squared y over dx squared, we can write it as d squared y. Extending the idea, the nth derivative can simply be written as d raised n. For example, if we consider the dE y double prime minus 4y prime plus y equals 0, we could write it as d squared y minus dy plus d raised 0 times y equals 0, which would imply d squared minus d plus 1 times y equals 0. The use of differential operators would come into play later on, especially in terms of notation and such. And then another important principle is the superposition principle. Suppose we have y1, y2, well, I should probably write it as y1 of x plus y2, y2 of x all the way up to yn of x are solutions to a homogeneous DE, then y equals c1 y1 of x plus c2 y2 of x plus c3 y3 of x all the way up to cn yn of x is also a solution on some interval I. We all know that a particular interval is what we call the existence interval. Here's C1, C2, all the way up to Cn. Are arbitrary parameters which can be solved using initial conditions. Now, if we have an nth order homogeneous equation, then we need n minus 1 initial conditions. So nth order DE, we have n derivatives, so we pretty much need for some a constant, an initial condition, another constant for the first derivative and the second derivative, and all the way up to the n minus first derivative. And if we have all those constants, then we if we have all those initial conditions, then we could solve for the constants. Here is a note for a homogeneous DE. If y1 of x is a solution, y2 of x equals some constant multiplied by y1 of x is also a solution. In other words, a constant multiple of a solution is a solution. Second point here, the trivial solution y equals 0 is always a solution to a homogeneous DE. For example, suppose the DE is y double prime minus y equals 0. Of course, this is homogeneous, and the trivial solution is y equals 0. And if we plug that back in the original DE, if y is 0, y double prime is 0, and we already know that y is 0. So 0 minus 0 is 0, and the equation is satisfied. So the trivial solution will always be a solution to the homogeneous linear DE. And a concept that we have to keep in mind is called linear dependence. Suppose y1 of x, y2 of x, y3 of x, all the way up to yn of x are solutions to a DE. Then we know from the superposition principle y of x equals c1 y1 of x plus c2 y2 of x plus c3 y3 of x all the way up to cn yn of x. Now that is the superposition principle. The solutions that we have, which are y1 of x, y2 of x, y3 of x, yn of x, are linearly independent if y of x equals to 0 only when c1, c2, c3 all the way up to cn is equal to 0. The only way the solution y of x would be 0 is when every single constant is 0. And if we have that, then y1 of x, y2 of x, all the way up to yn of x are linearly independent. Let's say, as an example, y1 of x equal to x and y2 of x equals 2x, linearly independent. Well, just by looking at it, they're not, because you've got x here and x there also, and they are dependent. But how do we make a case for it? Well, y of x, according to the superposition principle, would be c1x, the first solution, plus c2 times 2x. Now, if I pick appropriate values for c1 and c2, that particular equation would become 0. So if I choose c1 equals 2 and c2 equals -1, then y of x would equal 2x minus 2x, which is 0. So the solution becomes 0 for non-zero values of c1. The condition for linear independence is the solutions are linearly independent if y becomes 0 only when all of the constants become 0. And that is not the case. c1 here is 2, c2 there is -1, but the solution ended up being 0. So they are not linearly independent. If they're not linearly independent, we call them linearly dependent. It is easy to see that here, but what if we have higher order derivatives? That's where the Wronskian comes into place. The Wronskian W is a matrix which is defined like so. All the way up to the n minus first derivative. Of each of the solutions. That matrix is what we call the Wronskian. So the solutions y1 of x, y2 of x, y3 of x, all the way up to yn of x are linearly independent if the determinant of the Wronskian is not equal to 0. So that is the condition we use to determine if the solutions are linearly independent. A set of linearly independent solutions to a homogeneous DE is called the fundamental set of solutions on some interval I. And if we know that we have a fundamental set of solutions, then, of course, the solutions are linearly independent, then y equals c1 y1x plus c2 y2x plus all the way up to cn yn of x is called, or is the general solution of the homogeneous DE. So here we have a family of solutions. We should know what a family means, and we call it a family because if we change the values of C1 and C2, we're going to get a whole bunch of solutions. So all of these solutions together would form a family of solutions. So if we have a differential equation, y double prime minus y equals 0, obviously this is a homogeneous differential equation. And they've given you the solution. And the existence interval is negative infinity all the way up to positive infinity. Now, we won't define the constants C1 and C2. Now, how do we find the constants? We make use of the initial conditions. As I mentioned earlier, if it is a second derivative, then we would like to have two initial conditions. One would be y of 0, the other would be y prime of 0. If we have a third derivative, then we would have three initial conditions. Did I write that correctly here? Okay. So I sort of made a mistake here. So we have n minus 1 initial conditions on the derivatives. On the n minus 1 derivatives, and 1 on y itself. Sorry about that. So here we have a solution to the IVP, and we have two initial conditions, one on the solution itself, which is y of 0 equals 0, and the other is on the first derivative. So if we have a third derivative, then we would have a solution on y, an initial condition for y, an initial condition for y prime, and an initial condition for y double prime. So how do we go about solving this? We know y of 0 is 0. This would imply when x is 0, y is 0. So 0 would equal to c1 e raised 0 plus c2 e raised negative 0, which would imply c1 e raised 0 is 1, e raised negative 0 is also 1. We end up getting c1 plus c2 equals 0. And we have y prime of 0 equals 1. So the first job is to find y prime. We have y to be equal to that expression, so y prime is c1 derivative of e raised x is e raised x, derivative of e raised negative x is negative e raised negative x. Now we plug in the initial condition. Y prime of 0 would equal to c1 e raised 0 minus c2 e raised negative 0. Y prime of 0 is simply 1, so 1 would equal to c1 minus c2. So we have an equation here and another equation there. So the constants can be found using the two equations. Going back to algebra, this would form a linear system of equations. So we have c1 plus c2 equals 0, c1 minus c2 equals 1. If I add the two equations, the c2's would go away. 2c1 would equal to 1, which would imply c1 equals 1/2. If c1 is 1/2, I could take c1 and plug it in one of the two equations. I'll plug it in the first equation. c1 is 1/2. 1/2 plus c2 would equal to 0, which would imply c2 is negative 1/2. Therefore, the solution to the IVP is y, replace c1, I have 1/2 e raised x, replace c2, negative 1/2 e raised negative x. You may leave it as is, or you could pull that 1/2 out and write it this way. So here we have a third order homogeneous equation. The right hand side is 0. They've given us the solution. And the existence interval is negative infinity to infinity. The initial conditions, we need 3 of them. 2 for the first and the second derivative because we have a third order homogeneous equation, and 1 on the solution itself. So the initial conditions are y of pi equals 0, y prime of 0 equals 2, y double prime of pi equals negative 1. So, of course, we need the first derivative here and the third derivative because the equation has those. So, and we have a condition for the second derivative. So let's go ahead and find the first derivative. Y prime, derivative of constant c1 is 0. c2 times the derivative of cosine x is negative sine x, plus the derivative c3 times the derivative of sine x, which is cosine x. So we have negative c2 sine x plus c3 cosine x. Now we've got to find the second derivative. Negative c2, derivative of sine x is cosine x. Derivative of cosine x is negative sine x, so we have negative c3 times sine x. So that would be the second derivative. And y is given in the problem itself, and y is simply c1 plus c2 cosine x plus c3 sine x. So let's plug in pi for x. So y of pi is 0, which would imply c1 plus c2 cosine of pi plus c3 sine of pi. We know that sine of pi is 0 and cosine of pi is negative 1. This would imply 0 is equal to c1 plus c2 times negative 1 plus 0, which would mean 0 is equal to c1 minus c2. We'll call that equation 1. Y prime of 0 is 2. We have y prime as negative c2 times cosine of 0 minus c3 times sine of 0, which would imply cosine of 0 is 1, sine of 0 is 0. So we have negative c2 times 1, negative c3 times 0 equals 0. 2. So negative c2 is simply 2, which implies c2 is negative 2. So we already know in equation 1, c1 minus c2 is 0. So plug in c2 equals negative 2 in c1 minus c2 equals 0, which would imply c1 minus of minus 2 equals 0. c1 plus 2 equals 0, which would give us c1 to be negative 2 also. And lastly, we make use of the third initial condition, which is y double prime of pi is -1, and we know y double prime is, aha, I made a mistake. I knew that things here got too easy. I apologize. Y prime of pi is 0. I actually plugged it in the wrong derivative, so you've got to be careful. So negative c2 times sine of 0 plus c3 times cosine of 0 would equal 0, which would imply 0 plus cosine of 0 is 1, c3 equals 0, which would imply c3 is simply 0. Lastly, we have y double prime. Oh, it's not 0, it's 2. So simple mistakes could get you in trouble. So c3 is 2. And lastly, we go on to y double prime of pi, which is -1. Plugging it in the second derivative, we have negative c2 cosine of pi minus c3 sine of pi. Sine of pi is 0, cosine of pi is -1, so negative c2 times -1 plus 0 is -1, which would imply c2 is -1. Plugging c2 in equation 1, we will get c1 minus of -1 equals 0. c1 plus 1 would equal to 0, which should imply c1 is -1. So we found the three constants. So the general solution I'm calling it the general solution because each of these are linearly independent. So the constant is independent from cosine of x and sine of x. They're all linearly independent. They form a fundamental set. So fundamental set of solutions, when you put it as a linear combination, would give you the general solution. So the general solution would be y equals -1. C2 is -1, so -1 times cosine x. C3 is 2 plus 2 sine x. I don't like to start with negative things, so 2 sine x minus cosine x minus 1. So here we have a boundary value problem. A boundary value problem, we've seen this before, is similar to an initial value problem, but the only difference is instead of specifying the conditions for each of the derivatives and the solution y, we pick the solution and put it on an endpoint and define it on endpoints. So here the boundary is between 0 and pi. So we're defining the solution to be a certain way between 0 and pi. And those two would form the endpoints of the solution, and hence we call it the left and right boundary of the solution. Therefore, the problem here is a boundary value problem. So y double prime minus 2y prime plus 2y equals 0. Right hand side is 0. This is a second order homogeneous equation. Are the solutions linearly independent, y1 of x and y2 of x? So this would be y1 of x. That would be y2 of x. And you may look at it and say, oh, those two terms have cosine of x, so they have to be linearly dependent. But if you pay close attention, this has e raised x and that has e raised negative x, which would make them linearly independent. So wonderful. So now we have the boundary conditions. Y of 0 is 0 and y of pi is 1. So we don't have to find derivatives in this case. So y of 0 is 0, which would mean we are going to plug in x to be 0. We know cosine of 0 is 1, so c1 plus c2. And e raised 0 is also 1, so c1 times 1 plus c2 times 1 would equal 0. So the first equation is c1 plus c2 equals 0. I'll call it 1. Y of pi is 1, which would imply c1 e raised pi cosine of pi plus c2 e raised negative pi cosine of pi equals 1. We know that cosine of pi is negative 1, so c1 e raised pi times negative 1 plus c2 e raised negative pi times negative 1 equals 1. So negative c1 e raised pi negative c2 e raised negative pi is equal to 1. That would be the second equation. From the first equation, c1 plus c2 is equal to 0, which would imply c1 is negative c2. So I'm going to plug that in number 2. So minus c2 times minus e raised pi minus c2 e raised negative pi would equal 1, which would mean c2 e raised pi minus c2 e raised negative pi equals 1. c2 times e raised pi minus e raised negative pi would equal 1, which would imply c2 is 1 over e raised pi minus e raised negative pi. We already know that c1 is negative of that, so c1 is simply negative 1 over e raised pi minus e raised negative pi. So the general solution is y equals plugging in c1 multiplied by e raised x cosine x, c2 e raised negative x cosine x. We can see that once we plug in the boundary conditions, these terms become common. So I could pull those out. So cosine x over e raised pi minus e raised negative pi, negative cosine x negative e raised x positive plus e raised negative x. I don't like to start things with negative stuff, so cosine x divided by e raised pi minus e raised negative pi multiplied by e raised negative x minus e raised x. Well, I don't want to start with negative things, but e raised negative x is negative, has a negative, but whatever. So here we have another boundary value problem, but if you look at this, in this case we're defining the boundary for y of 0 and y prime of 1. So we are fixing the first derivative at 1 and the original solution at 0. Now, is that dE homogeneous? This is a non-homogeneous second order dE on negative infinity to infinity. We don't have to know about non-homogeneous dE because we're simply trying to find the solution to this. In the next video, we will talk about non-homogeneous dEs and the general solution and the particular solution and so forth, whose solution is y equals c1x squared plus c2x raised 4 plus 3. We need to find the first derivative because one of the conditions is defined on the first derivative. So the first derivative would be derivative of x squared is 2x, so we have 2x c1. Derivative of x raised 4 is 4x cubed, so 4x cubed times c2. Derivative of the constant is simply 0. So we plug in the conditions. Y of 0 is equal to 3. So if I plug in 0, I simply end up getting y equals 3, which should make sense. Y prime of 2 is 2, so 2 would equal to 2x c1 plus 4x cubed c2, and we are plugging it at 1. So 2 times 1 c1 plus 4 times 1c2 would equal to 2. This would mean 2 equals 2c1 plus 4c2. We have a 2 in common, so if we divide by 2 on both sides, 1 equals c1 plus 4c2. This would mean c1 is 1 minus 4c2. We could take that and plug it in the solution. We get y equals 1 minus 4c2 x squared plus c2 x raised 4 plus 3. Note, we reduced a 2-parameter family of solutions with C1 and C2 to a 1-parameter family of solutions with only C2. Why is that the case? Well, we simply have two boundary conditions. This should be boundary. So this happened because we don't have enough conditions to find the general solution. So we require one more condition for the solution.